This will be a second lecture on exponent power rules in astronomy. This one will use Kepler's third law again. There's a previous lecture on this that you may want to watch for some background material. And this time we're going to look at situations where we happen to know the orbital period of something and we'll figure out the semi-major axis. Kepler's third law is the relation that we have right here. P squared equals CA cubed. I've got the P, the A, and the C described here. P is the orbital period, how long it takes something to orbit the sun in years. A is the semi-major axis of the object's orbit. The orbits are elliptical. The long axis of the ellipse is called the major axis, and half of that is the semi-major axis. And then there's that constant C, which in the previous lecture we found out that it had a value of C is equal to 1 year squared per AU cubed for things orbiting the sun. And I mentioned in that previous lecture of a comet back in the late 1990s that had been reported to have an orbital period of 14,000 years. Well, when I looked up the article on that comet on Wikipedia, it turned out after better measuring the orbit of the comet, the original orbit of the comet had a period of 17,000 years. The comet was called Hyakutake. It was named after the astronomer who discovered it, a Japanese astronomer, amateur astronomer, who actually discovered it with binoculars, fancy binoculars, but still just binoculars. Its orbital period on the previous orbit was found to be 17,000 years. And we can calculate what the semi-major axis of the orbit would be for a comet that has an orbital period of that. So let's see how to do that. P squared equals CA cubed. It's the A that we're after, so we'll solve this equation for A cubed first, just dividing both sides by C, and you would get A cubed equals P squared over C. Plug in the numbers here. 17,000 years, and we're going to square that, divided by C. Now, several times in this lecture we're going to be doing this where we'll have two quantities multiplied together in parentheses and we square them, and we're using this rule that when you have two things multiplied together raised to a power, they each get raised to the power. So that's one of our rules for exponents. So here I'll have 17,000 squared and years squared. The years squared, I'll just write it as y squared. I have to do that 17,000 squared on my calculator. And I'm going to find it advantageous to use scientific notation from here on out. When I square 17,000, I get 2.9 times 10 to the 8th. And I'm only keeping two significant figures because in that 17,000 I can only see that there are two for sure. And then I've still got the years squared. Now down here on the bottom, I'm going to put in that value of C, which is 1 year squared per AU cubed. And I'm doing something here with the units. If I just look at the units, I've got years squared on top and years squared over AU, astronomical units cubed, on the bottom. When you divide by a fraction, you flip the fraction and multiply by it. So I'll have on top years squared, I multiply by AU cubed over years squared, and you can see the years squared divide out, and I just get AU cubed. So what I now have here is A cubed is 2.9 times 10 to the 8th AU cubed. But I want A. I want to know what the value of A is, the size of the semi-major axis. I raise both sides to the 1/3. When I do that, on the left side, a power to a power, I multiply the exponents. 3 times 1/3 is 1. I just have plain old a on the left side. On the right side, I've got two things multiplied together, raised to a power. I'll have to have 2.9 times 10 to the 8th raised to the 1/3, and au cubed raised to the 1/3. Well, that au cubed to the 1/3, 3 times a third is 1 again, so I'll end up with some number that's just going to have au for the units. Then I have to raise that 2.8 times 10 to the 8th to the 1/3. Here are the keystrokes. I'm going to rattle through it here. I'm not really teaching you how to use a calculator too much, but I'll show you what the keystrokes are and then I'll talk about them. Okay, I've listed the keystrokes here. Anything that's hitting a button other than just plain old numbers, I've put boxes around. First thing I have to do is put something into the calculator in scientific notation, and that's what this does. The 2.9 second x to the -1 button, this is on a TI-30X2, that's the process you go through for putting in a number that way. And when you do that, everything that I've got in the bracket there gets tied together as a single number. If you try it by any other way, the numbers are treated as separate parts, the exponent and the multiplier of the thing, and it won't work real well. So that's something that I have to do there. That's just putting it in scientific notation. This right here, the caret key, is how I raise something to a power that may not be a nice integer or may not be just squared. Actually, the only thing built into this calculator is squaring something. So I have to do that. And I want to raise it to the 1/3, but in order to tie all of that 1/3 together as a single number, I have to wrap it in parentheses, otherwise I'll get order of operations errors. And so all of this is just producing a 1/3, left parenthesis, 1 divided by 3, right parenthesis. So there's my exponent, and then I hit the equal key. And those are my keystrokes for doing this. So I'll calculate that now. And when I do that calculation to two significant figures, I get 660 astronomical units. So this is a pretty good-sized orbit. For Earth, the value of A, its semi-major axis, is just 1 astronomical unit. In fact, that's the definition of an astronomical unit. For what is now considered the most distant planet, which is Neptune, the value of A is about 30 astronomical units. For the object formerly considered a planet called Pluto, its orbit was about 40 astronomical units. So you can see this comet had a much larger orbit than either of those two things.